Okay, when we left off, we were talking about an example where we had 3 different spheres attached to a massless rod. So the moment of inertia, which we found in part A, was found by taking this rod, this mass's distance, r, squared times the mass of 3. And then we added this distance squared times the mass of 2. And then we added this distance squared times the mass of 5. You add it all up to get the total moment of inertia, or the total rotational inertia, and we got this value. Then we had to find the rotational kinetic energy of the system. We know the formula required is 1/2 I times omega squared. And we know what I is. That's what we found in the prior part. To find omega, we had to convert our revs per second into radians per second. The way we do that conversion is we multiply by 2 pi radians per 1 revolution. This is the number of radians that we sweep out in 1 revolution. The revs cancel out. You multiply 3 times 2 pi, or 6 pi, and so now you've got 0.2408. That's the value of I from above. And we're multiplying 6 pi squared. You square everything. You got to distribute that to everything in parentheses. And when you calculate this out, what is it? It's 42.8 joules. The unit is joules, just like other forms of energy. For part C, rotational kinetic energy is the energy that an object has when it is spinning about an axis, like this. By contrast, translation, so this is the act of rotating. This is rotation. By contrast, translational kinetic energy, that's the 1/2 mv squared, it refers not to spinning at some rate omega. Instead, it refers to the energy an object has when it's moving along the x, y, or z axes. So, x, y, z. And so if an object is actually traveling from one point in space to a different point in space, that's translation along the x, y, and or z axes. Okay, on the next page, let's say we've got a ball that's released from rest at the top of a hill, and it rolls down. As it goes down, it loses the initial height that it has. So what's the energy associated with height? Well, when it's up here, it has gravitational potential energy given by the formula mgh. When it gets to the bottom, it's moving with translational motion. So it has kinetic energy at the bottom. But it's also rotating now, because this is a ball that's rolling down. It's not slipping, it's just rolling down. So if it has a final speed, then it also has a final omega, because v equals omega times r. So we also have rotational kinetic energy. The formula for kinetic energy is 1/2 mv squared. The formula for rotational kinetic energy is 1/2 I times the angular speed squared. And what's the difference again? Well, translational motion, the 1/2 mv squared, is moving along the x, y, or z axes. And rotation is when an object is just spinning about an internal axis. So we can move this over a little bit. That's rotation. To take a moment to describe the energy transformation, remember this is turning into, or transforming into, these two things. Be sure to distinguish translational Translational. Distinguish that from rotational when you answer this question. Now let's look at part D and compare the forces. So I want to first consider this ball as it goes down. Here it is, midway. And then I want to compare that to a block sliding down without friction. Well, we know that gravity acts on both. And let's say that they have the same mass, so they have the same gravity force. I haven't drawn any arrow longer because the mass and force are the same. We also have the normal force, which will be the same for the two objects. And you might recall that we could break gravity into its components. There's a component perpendicular to the ramp and a component of gravity parallel to the ramp. So the component, if I redraw it, it's parallel to this ramp surface. And let me draw those here. The angle of the ramp of the incline, theta, is the same as this top angle. That can be shown pretty easily using similar triangles. We're not going to go through the exercise here. mg is the black, that's the hypotenuse. Here's our right angle. And so this leg is adjacent theta. So this is mg cos theta. And so the normal force balances with mg cos theta. This leg over here is opposite the angle. See how that leg here is opposite theta? So this is mg sine. Hypotenuse sine theta, because it's opposite. Likewise here, we can make those labels, mg cos and mg sine. And the normal force points off the ramp, perpendicular to the surface, always. The normal reaction. So this doesn't have any friction, so we're done. That's the whole picture. But right here, remember which way this thing is spinning. Let's draw an arrow showing which way it spins. It's going down, so it's spinning like this as it rolls down. So if it's spinning like that, but it's speeding up, which way does the friction force have to point? Well, to speed this thing up, friction would have to point with the rotation. It's static friction because the thing is not sliding. It's gripping the ramp, gripping the incline. That's why it doesn't slip and slide, because it has grip, traction. That's what allows it to roll down without slipping. So the static friction is with the rotation in order to speed up the rotation. So look at this, the net force. Well, when we consider the net force, these cancel. We can get rid of mg because we broke it into components. So the net force is you've got this component that does not cancel. That's going to be positive because it points down the ramp. Mg sine theta. And then we've got this static friction force that does not, that points up the ramp, so it's opposing the motion. We're going to make that negative. Over here, we can get rid of mg because we've broken it into components, resolved it into the components. Mg cos theta and n, they balance, so there is no net force on the y-axis. And on the x-axis, our net force is just this bottom one, mg sine theta. That's the only force that doesn't cancel. That's the net, the unbalanced force. So this is really interesting. There is a bigger net force on the right in this case. And my challenge to you, remember what we said when the object is rotating, the PEG is converted into translational KE and rotational KE. If there is no rotating, the PEG simply converts or transforms into translational kinetic energy. Maybe I should give that a T. Translational. And so, does this make sense? Why does a smaller net force make sense given this equation? Why does a bigger net force make sense given this equation? I challenge you to consider that question.